Let's talk about how to factor polynomials. In your review from Algebra 2, there were different types of techniques that you could use. Quadratic patterns, which was factoring x to the second power, which you're going to extend to x to the fourth power. Circle, slide, divide, which means if your leading coefficient was not 1, but it was 2, 3, 4, or 5. Grouping, greatest common factor, which, by the way, that's what we always start with. So this should be step number 1, greatest common factor. But then we also learned in Algebra 2 how to factor cubics, sum and difference of two cubes, as well as difference of two squares. We're going to abbreviate the difference of two squares as DOS, and we're going to abbreviate the sum and difference of two cubes as SOC and DOC. So let's take a look at these different factoring techniques. First one to review is quadratic patterns. Remember, when you're dealing with a quadratic, that's x to the second power, and we're dealing with a trinomial where the last term is positive. If the last term is positive, the only way that we can end up with a positive answer is if we are multiplying two positives together or multiplying two negatives together. So when we go to find unique factors for the trinomial, x squared plus 5x plus 6, we know that our leading term in our linear binomial is going to be x. And now what we need to do is determine our signs. Once again, since our last term is positive, we either have two positives or two negatives. Looking at our middle term's value, it's positive, so we're going to end up with positives in both binomials. Now we need to find our constants. We need two numbers that multiply together that give me 6, but when added together give me 5. And that would be 3 and 2. So the unique factors for x squared plus 5x plus 6 are x plus 3 and x plus 2. Extending that to problem number 2, we have what looks like the same exact problem. However, we notice that our last term is negative. And if our last term is negative, since the last term is negative 6, we can still break this into two linear binomial factors with our leading term x in both. But now we need two numbers that multiply together and give us negative 6. So we know there's going to have to be a positive and a negative. Now this is a pattern. If our last term is positive, it's going to be two of the same sign. If our last term is negative, then it's going to be one of each, because a negative times a positive or a positive times a negative equals a negative. So with that being said, we need two numbers that multiply together. One's going to be positive, one's going to be negative. That when multiplied together give me 6, but when subtracted give me 5. And the two numbers that I come up with are 6 and 1, because 6 times 1 is 6 and 6 minus 1 is 5. Now the question becomes, where do we put the 6 and where do we put the 1? Well, that's really easy. Since my middle term is positive, obviously I want more positives than negatives, so I'm going to place the 6 with the plus and the 1 with the minus. Okay, so take a look at these first two problems. They look kind of similar, but their factors are almost completely different. Moving right along. In problem number 3, again, we're going to have two binomial factors. There are no greatest common factors between x squared, 6x, and 9. Our last term is positive, so we're going to have two of the same sign. But since that middle term is negative, they're both going to be negative. Our leading term is both going to be x. And now I need two numbers that multiply together and give me 9, but add together and give me 6. And that means that they're both going to end up being 3. Now when I look at these factors, I notice that they're the same. So I can rewrite this as x minus 3 squared. Very important that we notice how we can rewrite x minus 3 times x minus 3 as x minus 3 squared. Problem number 4, again, just practice. Last term is negative, middle term's positive, so I know I'm going to have a positive and a negative that I'm going to have to multiply together. I'm going to end up with x minus and x plus. I need two numbers that multiply together and give me 15, but when subtracted give me 2, and that would very simply be 5 and 3. Now I need to decide what goes where. Obviously, since my middle term is positive again, I want my larger integer to be with my addition sign, and there are my unique factors for x squared plus 2x minus 15. Now how can we extend the quadratic patterns? If we wanted to take a look at number 5, for example, we notice that we don't have x squared anymore, we have x to the 4th. Well, we can think of this, again, I'm just using this as an example, of x squared squared minus 10x squared plus 16. The reason why I'm bringing that out is our x could almost be x squared. Now what does that do for us? Well, I could rewrite this problem and treat this like it was x squared minus 10x plus 16. Again, I'm just thinking, can I rewrite this problem? Now if this would have been x to the 4th minus 10x to the 3rd, then I couldn't do this. But since it's easy for me to substitute in x squared for x, I can do this. I can make this substitution that will help me factor this. Now factoring this, my last term is positive. So I'm going to end up with two signs that are the same. In this case, they're both negative since my middle term is negative. And this is going to end up being x minus 8 and x minus 2, because 2 times 8 is 16, but 2 plus 8 is 10. Now again, this was a substitution that I used to help me factor this. Now what I need to do is come back over and finish my problem. Remember, we said that in essence x was being substituted for x squared. So therefore, we can simply take the x and it will become x squared minus 8 and x squared minus 2, and that would be the unique factors for x to the 4th minus 10x squared plus 16. Number 6, just practicing. Again, treating it like a quadratic pattern. My last term is positive. I know that my leading terms, instead of being x, are going to be x squared. Since my last term's positive, I need two of the same sign. My middle term's negative, so they're both going to be negative. And now I simply look for two numbers that multiply together and give me 36, but add together and give me 13, and that's 9 and 4. Now, when you start factoring higher order polynomials, there's always the possibility that you can continue to factor. And so we've used a quadratic pattern to come to our conclusion that we end up with x squared minus 9 and x squared minus 4. However, if we use the difference of two squares in our next step for each one of our factors, we can continue to factor this polynomial. X squared minus 9, x squared is a perfect square, 9 is a perfect square. So we can factor this into x minus 3, x plus 3 using the difference of squares technique. The same holds true for x squared minus 4. Since it's x squared being subtracted by 4, I can factor this into x minus 2 and x plus 2. And now I have my factors for the polynomial x to the 4th minus 13x squared plus 36. What about factoring cubes? Remember from your algebra days, you learned that you could in fact factor cubes. There were two techniques that hopefully you learned: the difference of two cubes and the sum of two cubes. I'm going to abbreviate them as DOC and SOC. Now if you remember, you can keep your signs clean when you factor cubes by using the same sign that you were given, then the opposite, and then always positive. Let me elaborate on that. If I have given a subtraction sign between my two perfect cubes, I'm going to keep that subtraction sign. That's what we mean by the same. Then the opposite, then always positive. Notice how that will be just a little bit different with the sum of two cubes. I'm going to start with my addition, then the opposite of that, and then always positive. Now notice how we end up with our terms. It's always a binomial times a trinomial. A to the third, well, the cube root of that would be a, and b to the third, the cube root of that would be b. So let's see if we can factor some of these perfect cubes down below. And again, there are many ways to factor cubics. This is just one technique, and again, I'm just reviewing for people who need to see the review of how to factor these different terms. Oops. There we go. So we end up with a to the third plus 8. A to the third is in fact a perfect cube, and 8 is also a perfect cube. I'm going to rewrite this as 2 to the third power so you can see that the perfect cube for 8 is 2 to the third power. So now we need our binomial and our trinomial. And so keeping my sign the same, addition, opposite, always positive, and now inserting my cube roots, so to speak, we get a and 2 as our first two terms in our factor. Now how do we figure out the rest of these? Well, the pattern's really quite simple. We're going to square, and then we're going to multiply, and then we're going to square. Let me explain. Square the first term, a squared, multiply the two terms together, 2a, and then we're going to square 4. And there are the factors for a to the third plus 8. Let's see if we can work this problem. You may want to stop your video to work problem number 2. It's going to be a binomial and a trinomial. Sign is the same, opposite, always positive. Now again, 27 is 3 to the third power. X to the third is x to the third power. So as you can see, this is going to be x and 3. Now we're going to square, multiply, square. And there's my factored form. A couple of extra ones. Again, you may want to stop the video to work these problems. If I take 8x to the third, I can rewrite that as 2x to the third power, and 27 as 3 to the third power. Now I don't have to do this step. This just helps with my factoring. Again, with my signs, it's the same, opposite, always positive. So now it's 2x and 3. Now why is that? Because 2x to the third power is 8x to the third. Okay. Now I'm going to square, multiply, and square. Let's work this last problem. Again, you could pause the video if you'd like to do it yourself. Again, I can rewrite 64 as 4x to the third power, and of course the 1 is just 1 to the third power. Keeping my signs clean, same, opposite, always positive, 4x, and then the 1, and now I'm going to square, which is 16x squared, multiply, and square. And that's how you factor perfect cubes. Let's not forget our two techniques. Difference of two cubes we're going to call doc, and sum of two cubes we're going to call soc. Then there's the technique called the master product. The master product is basically our circle, slide, divide. Now for those that have forgotten what circle, slide, divide is, we're going to use a technique to help us with our quadratic patterns. You see, our leading coefficient here is not a 1, it's a 3. So what we're going to do is multiply the 3 and the 4 together to give us a new quadratic that we can use to factor that will help us with the final factorization of our problem. So we're going to end up with x squared minus x minus 12 after we multiply. So we circle and we slid. When we slide, we really are going to multiply. Okay? And now we're going to multiply this new, or factor this new quadratic. Using our quadratic patterns, our last term's negative, so it's going to be x minus and x plus. We're looking for two numbers that multiply together and give us 12, but subtract and give us 1. That's 4 and 3. I want my middle term to be negative, so obviously the 4 is going to go with the negative and the 3 with the positive. Now we would be finished with this problem except for one thing. Remember, this was a substitute to help us factor the original problem, so I need to do something with this 3. And the last step is to divide. So what we're going to do is take the 3 and divide by both the 4 and the 3 are constants. Now if it doesn't evenly divide, it's going to go back out front, and we're going to be left with 3x minus 4, and since 3 divided by 3 is 1, it's x plus 1. So let's take a look at number 2. Again, my leading coefficient is not a 1, so I'm going to circle and I'm going to slide or multiply, generating a substitute quadratic that we will use to help us factor the original problem. Using my quadratic patterns, my last term's negative, so it's going to be 1 positive and 1 negative. And now I'm looking for two numbers that multiply together and give me 30, but subtract and give me 7. That would be 10 and 3. My middle term's positive, so I'm going to put the 10 with the addition and the 3 with the subtraction. Now once again, I'm not done. I have to now take what I multiplied by and divide it out. So I'm going to divide by the constants. Again, since it evenly divides, this is going to become x plus 2. And since this will not evenly divide, we're going to bring it back out front. And there are my final factors, x plus 2 and 5x minus 3. Taking a look at my third problem, again, you may want to turn off the video to work it. But we're going to circle. We circled the first number, and now we're going to multiply by our constant, which is 3. That's going to give me x squared plus 8x minus 9. And now I'm going to factor. Notice that we've gone from a leading coefficient of 3 to now a leading coefficient of 1, and that makes it an easier or simpler problem to factor. And so again, our last term's negative, so we're going to have both a positive and a negative. We're going to end up with x's as our leading terms in both binomials. Two numbers that multiply together and equal 9, but subtract and give me 8 is 9 and 1. So obviously the 9 is going to go with the addition sign because we want our middle term to be positive, and the 1 with our subtraction sign. And now we can't forget the 3. 9 divided by 3 is 3. But since we can't evenly divide here, the 3 comes back out front, and we're left with 3x minus 1. So the factored form of our trinomial 3x squared plus 8x minus 3 is x plus 3 and 3x minus 1. Now, as I stated earlier, when you're factoring in upper level math classes, usually you're going to be given problems like this, factor completely, which means you may have to use several techniques to completely factor the polynomial. In this case, we're just going to use quadratics to get the general idea. When I look at problem number 1, again, you always want to start with a greatest common factor. A greatest common factor is a factor that is shared by all of your terms. And in this case, as you can see, all three, the 12, the 10, and the 2, are divisible by 2. So when I divide out the 2 from each term, I'm left with 2 times 6x squared minus 5x plus 1. Now, as you can see, this part of my problem still can be factored further, or we're going to test to see if it can. Using circle slide divide, another technique, this would become x squared minus 5x plus 6. Now the question is, can I factor this? Okay, so we're going to figure out if we can factor this or not. Well, since my last term is positive, we're going to end up with two signs that are the same, so it's going to be x minus and x minus. I need two numbers that multiply together, that give me 6, but add together and give me 5, and that's 3 and 2. Again, I'm not done. I need to bring the 6 back in that I multiplied by. And as you can see in this example, there's nothing that's going to divide evenly, so I'm going to have to simplify, and you always need to simplify. Very, very important. So the 2 goes out front, and that's 2x minus 1. The 3 goes out front, that's 3x minus 1. So we end up with our final factored form of 2 times 2x minus 1 and 3x minus 1. And that is the factored form for our quadratic. Taking a look at problem number 2, again, you could pause the video if you wanted to. There is a greatest common factor again of 2. But notice this time I have 2 perfect squares. So now I can use the difference of 2 squares since they're subtraction. Now if this would have been addition, I would not have been able to do that. And I can continue to factor into x minus 12 and x plus 12. Now again, if you don't remember what the difference of 2 squares states, you have 2 perfect squares being subtracted. Now let's remember how you end up with a perfect square. You have to have 2 identical terms multiplied together, 2 identical factors. So both of them would have to be a in the first and b in the second. Now notice that this particular quadratic does not have a middle term. The only way that that could happen is if they cancel each other out. So you see, if you take b and add it to a negative b, that middle term is going to cancel itself out. And so that's why we have one addition and one subtraction. Once again, if you want to stop the video to work this last problem down here. But once again, notice that all 3 of my terms are divisible by 3. So this is just another way that I could work the problem. I could divide all 3 terms by 3. And when I do that, I end up with the quadratic 2x squared plus 9x plus 10. Can I factor this further? The answer to the question is yes, I can factor it further. I can factor it further by using circle slide divide. So this would become then x squared plus 9x plus 20. Again, keep in mind, I'm writing this off to the side over here because I wanted you to see that we are generating a new problem to help us, a substitute problem to help us factor what we consider a harder problem. Factoring this now, the x plus and x plus because my last term's positive, my middle term's positive, and 5 and 4 because 5 times 4 is 20 and 5 plus 4 is 9. Now I need to divide by 2. This is going to come back out front. The 2's back out front. And 4 divided by 2 is 2. So my final factored form is going to be 3 times 2x plus 5 times x plus 2. So again, when you're factoring in larger problems or multi-step factoring, always start with your greatest common factor first. It's kind of frustrating when you use another technique and you find out that there was a greatest common factor that you could have pulled out that maybe helped you make the problem a little bit simpler. Now, why are we learning all this? We're learning all this so that we can solve a polynomial equation by factoring. And it's really quite simple what we're trying to accomplish. There's a theorem that states that if you have two factors and they're multiplied together and they happen to equal 0, then by logical reasoning that means that either A equals 0 or B equals 0 or they both equal 0. The idea is it's impossible for you to end up with an answer of 0 if one of the two factors is not 0 itself. So keeping that in mind, if I can get my polynomial into factored form, then all I really need to do is set each factor equal to 0 and then solve. So all we're asking to do here is just one more step. I'm going to go through this very quickly. So I'm going to take the x plus 3, which is my factor, set it equal to 0. 2x minus 1, which is my factor, set it equal to 0. And x plus 5, which is my factor, and set it equal to 0. Now if I solve each one of these, I get x equals negative 3, x equals 1/2, and x equals negative 5. So my solution set would be negative 3, 1/2, and negative 5. So let's put it together now for a couple of problems here. Let's say that I have 4x squared plus 6x equals 0. Let's use our factoring techniques. Is there a greatest common factor? The answer is yes. Both 4 and 6 are divisible by 2. X squared and x are divisible by x. So if I pull out my common factor of 2x, I'll be left with 2x plus 3. But both of these are factors. So I will set both the 2x equal to 0 and the 2x plus 3 equal to 0. I end up with x equaling 0 and x equaling negative 3/2. So my solution set is 0 and negative 3/2. What happens if I end up with a problem that we've already worked? Earlier, we factored the left side of this into x minus 3 times x minus 3, which we said we could rewrite as x minus 3 squared. We'll eventually learn that since we wrote it this way, something interesting is happening with the polynomial graph. This is a repeating factor, or a double root. We also would call it a multiplicity of 2 at the value x equals 3. So what we could still do, though, is take the x minus 3 and set it equal to 0, so x equals 3. And if you wanted to, it just means that the roots repeat, but we really don't need to repeat them. We can just say our answer is 3. We've already factored problem number 4 earlier in our discussion. This would factor into x squared minus 8. There we go, sorry about that. And x squared minus 2. Now again, how do I finish solving this? Set each factor equal to 0. Now of course when I do that, I'm going to end up with x squared equals 8, and I have to take the square root of both sides in order to solve this. Always simplify your square roots. So this is going to be x equals plus or minus 2 square root of 2. Finishing the second problem, add 2 to both sides. I end up with x squared equals 2. Now I'll take the square root of both sides, and I see x is equal to plus or minus the square root of 2. So my solution set is x equals plus or minus square root of 2 and plus or minus 2 square root of 2. There's 4 solutions. There should have been 4 solutions because my highest degree of my polynomial is 4. I hope this review helps you with going back over some of the factoring techniques you're going to need in order to factor higher order polynomials.